All right, today we're doing something really cool. We're going to take a journey to the very heart of reality itself. We're going to deconstruct matter, basically tear it apart piece by piece to understand how the simplest building blocks create everything from the device you're watching this on to the most distant stars in the universe. So what is everything around you really made of? Sounds simple, right? But the answer? Whoa, it's got layers. Just look around you for a second. You see solids, you're breathing a gas, maybe you've got a glass of water nearby, but what truly makes them different? And if we could just zoom in way, way down, what are the ultimate pieces? That's the journey we're on right now. Okay, so the first place to start, the most obvious way we classify all this stuff, is by its physical state. Now, we all learn about three of them in school, but there's a fourth, and get this, it's by far the most common one out there. The big difference between these states? It really all boils down to two things: energy and spacing. Think of a solid. Its particles are locked in a tight grid, just vibrating in place but holding a rigid shape. Now, add some energy. Heat them up. They break free and start sliding past each other as a liquid. It'll take the shape of its container, but its volume stays the same. Add even more energy, and those particles fly apart completely, becoming a gas, expanding to fill literally any space you give them. It's a perfect progression from order to chaos. And then there's plasma. This isn't just some superheated gas. No way. This is a whole other level. This is a state where there's so much energy that the atoms themselves get ripped apart, creating this supercharged soup of ions and electrons. It's the stuff that makes up lightning, neon signs, and, well, pretty much all the stars. And here's the kicker, the thing that totally flips your perspective. While we're living on this tiny little rock made of solids, liquids, and gases, almost everything else out there in the cosmos is plasma. Over 99% of it. Kind of rethink what's normal, doesn't it? Okay, so we've sorted matter by how it, acts, solid, liquid, gas. But now we gotta go deeper. We need to sort it by what it's actually made of chemically. And this right here is the first huge fork in the road for all of chemistry. Basically, everything, and I mean everything, can be tossed into one of two buckets. It's either a pure substance or it's a mixture. A pure substance like pure water or pure sugar has a fixed chemical recipe. It is what it is. A mixture, on the other hand, is just a physical jumble of different things, like salt water or the air. You can separate a mixture physically, boil the water away to get the salt back, but you can't do that with a pure substance. Now let's look inside that pure substance bucket. Turns out it's got two dividers inside. You've got elements, the absolute basic building blocks, the letters of the chemical alphabet. Think carbon, oxygen. You just can't break them down any further with chemistry. Then you have compounds. This is what happens when you bond those elements together to form new words with totally new meanings. Just think about it. Explosive hydrogen and breathable oxygen combine chemically to make water. The properties change completely. But let's be real for a second. Most of this stuff we deal with every day isn't perfectly pure, right? I mean, the air you're breathing, the coffee you might be drinking. We live in a world of mixtures. So what happens when you just kind of jumble different substances together? Well, these mixtures basically come in two main flavors. You've got your homogeneous mixtures, where everything is blended together so perfectly that it looks like one single thing. Salt dissolved in water is the classic example. You can't see the salt anymore, right? Then you have heterogeneous mixtures, where you can totally see the different parts. The easiest example, oil floating on water, or just a handful of dirt from the garden. But, this is where it gets really interesting. That line between perfectly mixed and obviously clumpy, well, it's not always a sharp line. It's really more of a spectrum. And that whole spectrum really comes down to one thing, the size of the particles being mixed in. At one end, you have solutions. The particles are tiny, molecular-sized. They're never, ever going to settle out. Way over on the other end, you have suspensions. Think muddy water. The particles are huge, you can see them, and if you let it sit, they'll all sink to the bottom. But right there in the middle, you've got this fascinating category called colloids. Think milk or fog. The particles are bigger than in a solution, but still small enough that they just stay suspended. They look uniform, but they've got a secret little trick that gives them away. And that secret trick? It's called the Tyndall effect. It's actually a really cool visual test. If you shine a light like a laser pointer through a glass of salt water, a true solution, the beam just goes straight through. You barely see it. But if you do the same thing with a glass of milk, a colloid, those bigger particles scatter the light and suddenly you can see the beam's entire path through the liquid. It's an awesome way to tell these mixtures apart. Okay, so we've sorted matter by its state,
We sorted it by its chemical makeup. Seems like we've got everything in nice, neat boxes, right? Well, nature loves to throw a curveball, and this one is a doozy.
And that curveball is a concept called allotropy. All it means is that you can take the exact same element, and just depending on how you arrange its atoms, you can get wildly different things. The best, most famous example of this involves a little element called carbon. So when I say carbon, you might think of this. You arrange those carbon atoms in a super tight, perfect 3D crystal lattice. And what do you get? The hardest natural substance we know of. A diamond. But what if you take those exact same carbon atoms, and instead you arrange them in flat sheets that can just slide right past each other? Well, then you get this. The soft gray stuff in your pencil that conducts electricity. Graphite. It's incredible, right? Same element, totally different properties. All because of the arrangement. And carbon is just showing off at this point, because it doesn't stop there. You can also get carbon to form these hollow, soccer ball-shaped molecules we call buckyballs, or even single atom-thick sheets of graphene, which is this ridiculously strong material. It's just the ultimate reminder that in chemistry, the recipe matters, but the arrangement is everything. So that leaves us with this final, kind of mind-blowing question. If the basic building blocks are actually this simple, how does just remixing them, bonding them, and arranging them in different ways create, well, everything? The entire complex, beautiful world around us? It's something to think about.